Okay, yeah. So sorry about the delay, but we finally have things sorted out, it seems. Maybe just move this over here, remove this, and turn this over to the side if I can. All right, so yeah, hello everyone. Today I'm going to be talking about modality matching matters, calibrating language distances for cross-lingual transfer in URIEL Plus. So today I'm going to be presenting with York. We're both undergrads from the University of Toronto, but really this was a kind of a global collaboration. We have people helping us from the US and even from Belgium. But yeah, without further ado, let's get started on the presentation. So the basic kind of setting that I want you to keep in mind throughout this presentation is as follows. Suppose that you want to do some kind of task in a low resource language like Haitian Creole. Like, obviously, we don't have that much information on Haitian Creole on the internet, so how do you really train a model to do that task, right? Your natural kind of instinct might be, okay, let's kind of train the model on some kind of high resource language and transfer, right? So two options, I don't know, maybe you think about French or Russian. I think obviously French is probably the choice here that you would immediately kind of consider because French is more similar. And so you choose that to train your model, right? But really, what did you actually consider in the back of your head when you made this decision? What you were really kind of considering is how distant or how similar are French or Russian to Haitian Creole, and the kind of implicit assumption or the implicit decision you made was that French was more similar to Haitian Creole, right? In other words, what you really needed was some conception of language distances. Now, in that case, we knew the low resource language, and so we could make a decision on which high resource language to choose. But in general, we want an ability to choose any kind of high resource language for any kind of arbitrary low resource language. And this can be like, for instance, any low resource language that you can think of. We want to be able to choose a appropriate source language to transfer from, right? And for that, again, we need some conception of a language distance. Now, in URIEL Plus, now in NLP, URIEL Plus is one of the kind of linguistic knowledge bases which has vector representations for languages, in particular in three different modalities. One of them is geographic, which basically represents where the language is spoken around the world. Genetic, which basically represents the shared ancestry on the language family tree, and typological, which basically represents differences in structure in the language. So this could be like grammar, phonology, phonemic inventory, so on and so forth. And there are 8,000 or so languages supported, each of them represented as a vector. And because they're represented as vectors, you can, in principle, compute distances between these vectors, which serve as a proxy for language distances, right? So these kind of language distances in URIEL Plus and URIEL, which is its predecessor, are widely used in downstream NLP tasks. So for instance, cross-lingual transfer, dependency parsing, MT, speech recognition, and even now recently LM regularization. I do want to give a special shout out to the papers that are highlighted in blue because these are papers at EACL 2026, which are using these language distances from URIEL or URIEL Plus. So clearly this is something that is used in the NLP kind of community, but there are some obvious flaws here, which York will talk about.
All right. I do want to give a big thank you to Aditya for talking about the utility of URIEL Plus. Now, you're going to have to forgive me a little bit because I will have to now talk about some of the limitations of your paper. So despite all of this, URIEL Plus's language distances have one fatal flaw, and that is that it treats all language representations uniformly, i.e. with high dimensional Euclidean vectors for all three modalities. And then URIEL Plus calculates language distances by the angular distance between those vectors. So how this might look like for each of the three modalities that we mentioned is, for example, for the geographic modality, the key assumption in URIEL Plus's vectors is that languages are spoken at a single point. So for example, English might be represented as a vector of corresponding to London and French, Paris, etc. And so we see that in this case, the language distances in URIEL Plus are extraordinarily small. And I hope this is clear that this is some sort of encoding some sort of Western-centric bias. For the genetic modality, the URIEL Plus's vectors contain over 3,000 features, and each of those features is a binary encoding of whether a language belongs in a certain language family. And aside from the high dimensionality, the key issue with a sort of Euclidean representation is that it assumes all language family splits to have equal weight. So for example, Hindi and German split at Indo-European, German and English split at West Germanic, and in URIEL Plus, this is assumed to have equal impact on the language distance. So what the result is for example, for these three languages, the language distance is unusually high, and this is, oh, sorry, I think your computer. Sorry, some issues with the power. Um,
Yeah, sorry, the technical difficulties continue. Just wait one moment, and then we'll get it right back rolling. Almost there. We should be back. Uh, mm, almost there, almost there, almost there. And just reshare. There you go.
So apologies for the technical issues there. So let me recap a little bit about the genetic modality. Overall, we see that the language distances between Hindi, German, and English here are unusually high, even though they are all part of the Indo-European language family. And then finally, for the typological modality, how do you? Okay. URIEL Plus's vectors include 800 features, and so obviously it's still very high dimensional. And the key issue here is that there are tons of correlated features in URIEL Plus. So for example, the syntactic feature of word order in URIEL Plus is encoded as multiple binary features. So we have one binary feature for SVO, one for SOV, one for VSO, etc. And we do see that in reality, the correlation between those features in URIEL Plus is substantially high. And so in my paper at EMNLP, we've already demonstrated that the high dimensionality of these representations do limit their effectiveness. But here in this paper, we make a more general, broader claim that language structures or language representations should match the structure of the modality that it is trying to represent. And so this is how we might do it with where for each modality, we now learn one new representation for each, that specifically serves that modality. And with these modality match representations, we can now calculate modality match distances. So here's an overview of sort of the representations that we learn for each modality, and I'll go over each of them in turn. For geographic distances, we want to account for the diversity of where a language is spoken. And therefore, we move from representing languages as a single point to now modeling the distribution of speakers for each language. Concretely, we measure for each language the proportion of speakers in each country. And this allows us to calculate the Earth mover's distance over distributions, and that gives us geographic distance. And so the benefit of this is that, for example, we were able to capture, say, how in the United States there are both English and Spanish speakers, where we know that there actually is a lot of language contact between English and Spanish. And so overall, this gives us much more realistic distances between English, French, and Spanish, as we can see here. Now, for the genetic modality, we study a different way of essentially embedding the glottolog family tree. Now, glottolog is a catalog of the world's languages, and part of what it encodes or what it provides is this family tree that gives us information on how languages have evolved. Now, URIEL Plus, as I mentioned, does this with a one-hot encoding of glottolog with binary features that encode whether a language is in a certain language family. And as I mentioned, this Euclidean approach flattens the language family tree and treats all shared ancestry to have equal weight. Instead, we now embed the glottolog tree in hyperbolic space. Now, the key intuition here is that language families, or the language family tree, grows exponentially with the number of descendants as we move down with depth. Now, the Euclidean space grows polynomially, and so it is unable to account for this sort of exponential growth, while hyperbolic space grows exponentially. And so we argue that hyperbolic space is really the natural geometry to use here when embedding the glottolog tree. And so this figure here shows us what that might look like for a 2D Poincare disk, where we have language families near the center and languages near the boundary of the Poincare disk. And this gives us, and the idea here is that this will give us much more realistic distances in terms of the genetic modality. And we do empirically verify that our new representation preserves hierarchy better by measuring the reconstruction loss for the glottolog tree, where our best model, which is a hyperbolic model with 10 dimensions, substantially outperforms the best Euclidean model in terms of MAP. And then finally, for the typological modality, while URIEL Plus contains high-dimensional vectors with groups of correlated features, we now group those groups of correlated features into latent binary variables, and we call these islands. Now, what each island is really is it contains some typological features where we believe that there really should be some kind of latent factor that governs those group of features. And concretely, for each island, we model the probability that it is the value of that island is 1, given the observed values for the features that it represents. And we learned this with a method called latent tree modeling, where we use a greedy algorithm and a Bayesian information criterion to iteratively build up clusters. And we see that the intra-island correlation, the average intra-island correlation in our neighborhood representation is 0.6, which is actually surprisingly high given the amount of noise that is present in URIEL Plus. And so this tells us that our islands actually capture something meaningful here. And finally, we now move on to evaluating how well our new representations actually are, or how well they perform for cross-lingual transfer. And so the task we study here is transfer language selection, where the idea is, as in our motivating example, let's start. Sometimes in NLP or multilingual NLP, we want to perform some sort of task in a low-resource language where we don't have enough data to train a model in it. However, let's say we do have other different models that have been trained in a different but high-resource language. And so our task here is to see how we can use language distances to predict the best model to use. And so the setup is this. Let's say we're trying to perform some sort of task, say text classification, where then we're given 4 things. 1, the unseen language that we are trying to perform classification in. 2, the language, some set of language models, each of them trained in a different high-resource language. 3, the performance scores of each of those models in text classification. And 4, the distances between our unseen language and each of those models. Now, then, given all of these things, we train a model called LangRank, which was developed by Lin et al. In 2019, that looks at these distances and is trained to predict the model that performs the best. So, and then we measure the performance of LangRank itself by a metric called performance loss, which we define as a relative gap in performance between the model that LangRank chooses and the best model. So concretely, a concrete example is, for example, for this task, LangRank chooses the French model, while the best model is Arabic. And so the French model has performance 0.7, the Arabic model has performance 0.8, and so the performance loss of LangRank in this case for this unseen language is 0.125. And then, so the overall idea here is that LangRank's performance, which we measure using this metric called performance loss, is dependent on the utility of our language distances for cross-lingual transfer. And so we want to measure how much our new representations impact language performance with an ablation study, where we switch out URIEL Plus's distances with ours when we train LangRank. And then we perform a regression analysis to determine how much our new representations actually impact language performance. And so here are the 9 tasks that we study, where the first 4 at the start here are essentially replicating the performance scores for dependency parsing, and linking, machine translation, and part-speech tagging that were already studied by Lin et al. And In the second group, these are the new tasks that we expand language evaluation from the original 2019 paper with, where in particular we have Taxi 1500, which we choose, which is a text classification task, which we choose high language coverage. And we also have SIP 200 and the new the new part of speech and dependency parsing task with the updated version of universal dependencies, which we choose and we choose these tasks to replicate the another study on language distances for transfer language selection by Blaschke et al. In 2025. And finally, we also replicate these tasks of XNLI according to the setup of Philippi et al. In 2023. And all of these, so the overall idea of our evaluation here is to replicate the setups of previous papers that have already studied the effect of language distances on transfer language selection. And so the table here shows the baseline row. So in the baseline row of our table, that represents the performance loss when we train LangRank using URIEL plus synthesis. And how you might interpret that, for example, is for the dependency parsing task at the top, the performance loss is 11.4. And that means that LangRank chooses the model that on average performs 11.4% worse than the optimal model. And so our goal here is to try to measure how much our language distances affect that. And so here are the results. And overall, we see that there is always, for each of these tasks that we study, there is always some sort of combination of swapping to our new distances that we can do to reduce the performance loss in those tasks. And that means that we're able to close the gap between the models that we choose and the optimal model. And some of the results here are actually really substantial. So if we look in the first group of the table, if we look at the hyperbolic representation, it reduces MT performance loss by 4.5 percentage points. And that is really a 36% decrease. And similarly, for the in the second group, for the ident representation in XNLI, it reduces performance loss by 39%. So all of these results are actually really substantial in terms of closing that gap. But we do caution that the performance impact of each of our modalities do vary across different tasks, and that there is no uniform, there is no modality or new representation that we learn here that uniformly reduces performance loss significantly. And so here are the takeaways of our paper. The first is that we argue that, or we claim that when we learn language representations, those representations should really be matched to the structure of the modality that we are trying to represent. And indeed, in our paper, we find that our structure-aware language representations do consistently outperform URIEL plus in cross-lingual transfer. But then we do note that the performance impact of our new representations are task-dependent. And so we argue that there really is still no one-size-fits-all solution to cross-lingual transfer. And this does echo the findings of previous papers such as Blaschke et al. In 2025, where we find that each of our new representations has a task-dependent impact on performance loss. And so we claim, or we at least we caution that our new language representations should not be used as a drop-in replacement where we just simply swap out everything with our new representations and expect it to perform necessarily better. And so that is the end. Thank you so much for listening to our talk. Here's the paper, here's our code, and our emails.